March 18, 1967. 14,000 feet above the jungle west of Da Nang Air Base, the F-4 Phantom shudders. Not from enemy fire, not yet, but from something deeper, something structural. The cockpit smells of hot metal and burned hydraulic fluid. Major Robert "Buck" Henderson, United States Air Force, tightens his grip on the control stick as the aircraft vibrates through a high-speed turn. It was never meant to sustain this often, this violently, this loaded. Below him, the jungle is alive. Tracer fire climbs upward in slow, deliberate arcs. North Vietnamese anti-aircraft guns are already tracking his escape path. Henderson banks harder. The G-forces press him into the seat. The aircraft groans. And somewhere inside the Phantom's airframe, beneath the aluminum skin, past the rivets and stringers, microscopic cracks are growing. Henderson doesn't know it yet. The engineers who designed this aircraft don't know it either. But Vietnam is about to expose a truth. No wind tunnel, no laboratory fatigue test, and no peacetime assumption ever revealed. That aircraft are lying. The Phantom clears the ridgeline and heads for the sea. Henderson makes it home. The jet lands hard, trailing smoke, one stabilator scarred by shrapnel. Ground crews swarm the aircraft, counting holes, measuring damage. On paper, the Phantom survived exactly as expected. But in the hangars, when the skin panels come off, the inspectors stop talking. Hairline fractures run through load-bearing members that were never supposed to crack, not at this hour count, not under these stresses. The aircraft flew. The aircraft landed, but structurally, it should not have. This is where the war quietly changes aviation forever. Before Vietnam, American aircraft design is ruled by controlled assumptions. Engineers calculate fatigue life based on predictable flight profiles, takeoff, climb, cruise, combat maneuver, landing. Stress cycles are counted, safety margins are generous. Damage is assumed to be binary, either catastrophic or cosmetic. Vietnam shatters that model. Aircraft here do not fly textbook missions. They loiter low and slow over jungle canopies soaked in heat and humidity. They haul asymmetric bomb loads. They yank into evasive turns again and again to escape fire. They land with partial hydraulic failures. They take hits, not enough to destroy them, but enough to wound them in ways no equation had accounted for. Each mission bends the airframe slightly. Each recovery hides another fracture. At Da Nang, Cam Ranh Bay, Ubon, Korat, maintenance officers begin noticing patterns. F-105 Thunder Chiefs returning with warped wing spars. A-4 Skyhawks showing fatigue cracking far earlier than predicted. Huey helicopters with stress fractures creeping along rotor hubs and transmission mounts after repeated high-load insertions. The aircraft are surviving combat, but they are aging years in months. Captain James Holloway, an Air Force maintenance engineer stationed in Thailand, stands under a stripped Phantom wing at Korat Royal Thai Air Force Base. He runs a finger along a fracture line barely visible to the eye. According to the manual, this wing should have thousands of hours left. According to Vietnam, it's already tired. Reports begin moving up the chain, not dramatic, not panicked, but persistent. Unexpected fatigue. Unusual crack propagation, components failing in combinations never seen before, aircraft returning safely that engineering logic says should have disintegrated in flight. And then come the crashes, not shootdowns, structural losses, jets breaking apart under maneuver loads that should have been survivable, helicopters losing rotor assemblies mid-flight after cumulative stress, pilots ejecting in disbelief, convinced they had done nothing wrong. The uncomfortable realization spreads quietly through engineering offices and program managers. The lab had been wrong. Not completely wrong, but dangerously incomplete. In the United States, back at Wright-Patterson Air Force Base and naval test centers, engineers begin pulling combat aircraft records, flight logs, G-loading histories, damage reports. They overlay real combat data onto pristine design models. The mismatch is undeniable. Vietnam is subjecting aircraft to irregular, chaotic stress patterns, short, violent bursts instead of smooth cycles. Battle damage introduces stress concentrations that accelerate fatigue instead of simply weakening strength. Tropical corrosion eats at aluminum bonds assumed to be protected. Field repairs change load paths in subtle but critical ways. The airframe isn't failing because it's weak. It's failing because the rules were written for a world that doesn't exist in war. And the most dangerous part is this: the aircraft don't warn you when they're about to give up. They keep flying right up until they don't. By late 1967, something unprecedented begins. Combat aircraft are no longer just weapons. They are data sources. Every crack is cataloged. Every failure is traced. Every impossible survival is studied. The war is forcing engineers to confront a new reality. Survivability is not just about armor or redundancy. It is about understanding how structures die slowly. And Vietnam is teaching that lesson in blood, aluminum, and silence. July 2, 1967. Cam Ranh Bay Air Base. The F-105 Thunder Chief sits nose high on its landing gear, panels removed, skin peeled back like a patient on an operating table. Major Glenn Foster, an Air Force structural analyst flown in from the States, kneels beneath the wing root with a flashlight and a clipboard. He has seen fatigue cracks before. This is different. The fractures are branching. Not a single clean crack, but a network, spidering outward from rivet holes, racing along stress paths that were never meant to carry this much load. According to every pre-war fatigue model, this wing should still be in the safe zone. According to Vietnam, it is already living on borrowed time. Foster flips through the aircraft's mission log. Low-level strike missions, heavy bomb loads, violent pull-ups after release, repeated exposure to ground fire forcing abrupt evasive maneuvers. Dozens of short, high-G events instead of smooth, predictable cycles. The math does not add up. Before Vietnam, fatigue life modeling is elegant and dangerously idealized. Engineers assume stress cycles are consistent, loads are averaged, peaks are smoothed out. The structure is treated like a patient jogger, not a sprinter forced into repeated sprints while wounded. Vietnam turns aircraft into sprinters. Every evasive break turns spikes stress far beyond cruise assumptions. Every asymmetric load shifts forces unevenly through the airframe. Every hit, even a small one, creates stress risers where cracks can grow exponentially. And none of that behavior exists in the original equations. At Naval Air Station North Island, California, similar alarms are sounding. A-4 Skyhawks returning from carrier strikes show premature cracking in wing attach points. Aircraft that should have lasted years are burning through their structural life in a fraction of that time. Engineers begin asking a question that feels almost heretical. What if fatigue is not linear? What if damage accumulates faster once it starts? What if battle damage doesn't just weaken structures, but accelerates their aging? To answer that, the military does something it has never done at this scale before. It feeds real combat data back into design analysis in near real time. Aircraft are instrumented, flight loads are recorded, damage is mapped and tracked across entire fleets. Maintenance officers are instructed not just to fix, but to document everything. A Phantom that survives a missile proximity blast is no longer just lucky. It is a case study. In laboratories back home, engineers rebuild airframes digitally and physically. They introduce irregular load spectra, chaotic spikes instead of smooth waves. They simulate corrosion. They introduce artificial damage and watch how cracks propagate under combat-like conditions. The results are unsettling. Structures fail sooner than predicted. Cracks grow faster once initiated. Redundant load paths behave unpredictably once damaged. The margin between flyable and catastrophic is thinner than anyone believed. One Navy report summarizes it bluntly. Combat usage invalidates peacetime fatigue assumptions. That sentence lands like a bomb, because it means every aircraft flying in Vietnam and every aircraft yet to be built is operating under rules that no longer apply. By late 1968, emergency measures are rolled out quietly. Inspection intervals are shortened. New reinforcement kits are flown into theater. Wing routes are strengthened. Critical joints are redesigned on aircraft already in service. Most importantly, engineers stop thinking in terms of safe life alone. Instead, a new philosophy begins to take shape, almost accidentally. Damage tolerance. The idea is radical for its time. Aircraft are no longer assumed to remain pristine until failure. Damage is expected, cracks are inevitable. The goal is not to prevent them entirely, but to ensure they grow slowly, visibly, predictably. So pilots can live. So maintainers have time. So structures fail gracefully instead of suddenly. Vietnam did not invent this concept, but it forced it into existence. Every Phantom that limps home on one stabilator. Every Thunder Chief that lands with a cracked fuselage frame. Every helicopter that survives overload after overload becomes proof that survivability is not binary. Aircraft do not simply live or die. They endure, and endurance must be engineered. By 1969, new analytical tools are emerging. Fracture mechanics moves from theory into practice. Engineers begin calculating crack growth rates, not just ultimate strength. Inspection methods improve. Non-destructive testing becomes routine instead of exceptional. Quietly, without headlines, the rules are being rewritten, not because someone wanted to innovate, but because Vietnam made ignoring reality impossible. And still the war has one more lesson to teach, one that will come not from jets, but from helicopters flying low, overloaded, and pushed beyond every limit ever imagined. October 14th, 1968. Landing Zone X-ray, Central Highlands of Vietnam. The UH-1D Huey drops through the mist, rotor blades biting humid air already thick with smoke. The helicopter is overloaded. Troops, ammunition, water, extra fuel lashed to the floor. Captain Alan Pierce, Army Aviation, keeps his eyes locked on the clearing below as tracer rounds snap past the cockpit. The Huey shudders violently as it flares. This is not how it was designed to fly. The Huey was built for mobility, not punishment. In peacetime testing, its limits are clear. Maximum gross weight, defined torque margins, controlled maneuver envelopes. Vietnam ignores every one of those limits daily. Pilots push harder. They have to. Hot temperatures reduce lift. High elevations steal power. Combat loads grow heavier with each mission. LZs shrink under fire. Takeoffs become vertical climbs at the edge of performance. Landings hammer the skids into uneven ground. Every flight loads the airframe asymmetrically. Every hard pull flexes the transmission mounts. Every evasive yaw twists the rotor mast. By the numbers, the Huey should be breaking apart, but it doesn't. At least, not immediately. Back at maintenance areas in Pleiku and Quy Nhon, mechanics begin noticing something strange. Hueys with thousands of combat hours are still flying, but only because crews are constantly chasing cracks. Tail booms show fatigue fractures near attachment points. Rotor hubs develop stress marks. Transmission decks show creeping deformation. Rivets work loose not from poor manufacturing, but from relentless vibration and cyclic overload. The helicopter is surviving by inches. The Army responds the only way it can in wartime, by learning fast. Field engineering teams are embedded directly with aviation units. When a crack appears, it is photographed, measured, reported. Temporary fixes are tested in theater, reinforcements are improvised, then standardized. One of the most critical discoveries comes from rotor systems. Pre-war analysis treats rotor loads as largely predictable. Vietnam proves otherwise. Rapid pedal inputs during confined landings, combined with gusts, heat, and battle damage, create torsional stresses far beyond modeled limits. Small imperfections amplify vibration, accelerating fatigue in hubs and masts. The response is not just stronger parts, but better understanding. Engineers begin mapping dynamic loads in real flight conditions. Sensors are installed, pilots are debriefed not just tactically, but mechanically. How hard did you pull? How fast did you flare? How heavy were you really? The data is brutal. Vietnam helicopters are living at the edge of structural failure every day. And yet, their survival reveals something crucial. The Huey does not fail catastrophically without warning. Cracks grow, vibrations increase. Components degrade gradually if someone is watching. This reinforces the same lesson learned from jets. The future is not preventing damage entirely. It is detecting it early. From this realization, new practices emerge. Mandatory vibration analysis, routine borescope inspections, component life limits based on actual usage, not theoretical averages. Redesigns that add fail-safe features instead of pure strength. By 1969, helicopters become flying laboratories. Every mission feeds data back into engineering models. The Army aviation community begins speaking a new language, one that blends pilot experience with structural analysis. It is no longer enough to ask, will it hold? Now the question is, how will it fail, and will we see it in time? This philosophy spreads beyond helicopters. Fixed-wing programs adopt similar thinking. Aircraft are no longer designed just to meet a load. They are designed to survive misuse. Vietnam is forcing designers to confront the truth no one likes to admit. Combat pilots will exceed limits, weather will lie, and damage will happen. So structures must be honest. By the end of the decade, the consequences of these lessons are already visible. New aircraft programs begin with damage tolerance baked in. Inspection access is prioritized. Redundancy is treated as survival, not weight. And somewhere in the jungle, another Huey lifts off, its airframe scarred, reinforced, and still flying, not because it was perfect, but because Vietnam taught America how to listen when metal begins to complain. January 11th, 1970. Wright-Patterson Air Force Base, Ohio. Snow coats the runways outside, but inside Building 65 the air is tense and warm. Engineers from the Air Force, Navy, and major aerospace contractors crowd around a long table layered with photographs, fracture diagrams, and flight load charts pulled directly from Vietnam. This is not a victory briefing. It is a reckoning. On the wall, a slide projector throws up the image of an F-4 Phantom wing spar, cracked nearly through. Another slide follows, same aircraft, still flown safely for 2 more missions before the damage was detected. Then a Huey transmission mount, distorted but intact. Then an A-4 Skyhawk with asymmetric damage that should have induced uncontrollable roll but didn't. Each image carries the same implication. The aircraft survived not because the rules worked, but because reality was kinder than theory. That is not a margin anyone wants to rely on. For decades, aircraft design has centered on safe life philosophy. Components are designed to last a predicted number of cycles, then be retired before failure. It assumes controlled usage and clean structures. Vietnam has obliterated that assumption. Combat aircraft are damaged early, stressed unevenly, repaired imperfectly, and flown far outside expected profiles. Safe life does not fail gracefully under those conditions. It fails suddenly. So the engineers in that room begin rewriting doctrine, not in dramatic declarations, but in requirements. New language enters official specifications: fail-safe design, damage tolerance, inspectability. These are not buzzwords. They are demands, written in response to wreckage reports and pilot funerals. The idea is simple and radical. An aircraft must be able to survive damage it is guaranteed to suffer. That means structures with multiple load paths. It means cracks that grow slowly and predictably. It means giving maintainers access to critical areas instead of sealing them behind smooth skins and optimistic assumptions. One Navy engineer puts it plainly during the meeting: combat doesn't ask permission from your stress model. This shift affects everything. Wing spars are redesigned with crack stoppers. Fuselage frames are reanalyzed to prevent cascading failures. Materials are chosen not just for strength, but for fatigue, resistance, and corrosion behavior in tropical climates. Even maintenance doctrine changes. Aircraft are no longer grounded simply because a crack exists. They are evaluated, measured, monitored, flown with restrictions if necessary. This keeps aircraft in the fight, but more importantly, it keeps pilots alive. Vietnam forces another uncomfortable realization as well. Laboratory testing itself must change. Full-scale fatigue tests become more aggressive. Instead of smooth cyclic loads, engineers introduce variable spectra that mimic combat abuse. Battle damage is simulated mid-test. Corrosion is added early, not as an afterthought. The structure is not allowed to live in a perfect world. It must survive the real one. By the early 1970s, these lessons begin shaping aircraft that will never see Vietnam, but are born from it. The A-10 Thunderbolt Sao Dinh, conceived later, is designed explicitly around damage tolerance, redundant control paths, titanium armor, structures that assume hits, not avoid them. The F-15 and F-16 incorporate fracture mechanics from the start. Inspection intervals are baked into design. Engineers ask not how strong, but how long after damage. Even civilian aviation absorbs the lesson. Wide-body airliners adopt damage-tolerant standards directly influenced by combat findings. Passenger jets become safer because combat aircraft once cracked quietly over jungles. Back in Vietnam, the war grinds on. Aircraft continue flying, Cracks continue forming, but fewer pilots die from sudden structural failure. Not because Vietnam has become less violent, but because engineers finally stopped pretending violence was an exception. By the time the war draws toward its end, America's aircraft are no longer designed under illusions of control. They are designed with humility. Because Vietnam taught the most unforgiving lesson of all: structures do not fail when equations say they should. They fail when reality decides it's time. And the only defense against that is engineering that expects the worst and plans for survival anyway. April 23, 1972. 18,000 feet over North Vietnam. An F-4 Phantom limps south, trailing a thin ribbon of smoke. Lieutenant Commander Mark Ellis, U.S. Navy, feels the aircraft fighting him. Not violently, not yet, but subtly. The jet responds a fraction of a second late to roll input. The warning lights stay dark. The gauges look normal. Experience tells him this is not a system failure. It's structural. Ellis reduces speed and eases the Phantom toward the coast. He does not yank the stick. He does not trust the aircraft to forgive impatience. Somewhere in the wing or fuselage, something has changed, and the difference between landing and ejection is whether that change grows suddenly or slowly. He lands. On the ground, inspectors find a crack that would have gone unnoticed 5 years earlier. It hasn't failed. It hasn't even reached a critical length. But now, thanks to lessons carved out of thousands of missions like this one, it is seen. That is the difference Vietnam made. By the early 1970s, aircraft are no longer judged solely by whether they survive a mission. They are judged by how clearly they reveal their own weakening. The philosophy that emerged under fire has become permanent doctrine. Safe life thinking does not disappear, but it is no longer trusted alone. Damage tolerance becomes law. New military standards require engineers to assume cracks exist from day one. Structures must tolerate them. Inspection access is mandated. Load paths are duplicated. Failures must be progressive, not sudden. The idea of a perfect airframe is abandoned. In its place stands something more realistic, a wounded one that keeps flying. This shift changes how engineers think, not just about metal, but about pilots. Human behavior is now part of the model. Designers assume pilots will pull too hard, land too fast, fly too heavy. The aircraft must survive human urgency. Vietnam forced that humility. At design reviews, engineers now ask questions that would have sounded pessimistic before the war. What happens if this spar cracks at 20% life? What happens if corrosion starts early? What happens if this repair is done in the field, imperfectly? Those questions save lives. They ripple outward. Training syllabi change, maintenance culture shifts from reactive to investigative. Aircraft are tracked as individuals, not interchangeable machines. Each tail number carries a history of stress and damage. The war ends, but the data does not. Boxes of reports, photographs, and fractured components remain in archives and laboratories. They are studied again and again as new aircraft are designed. Vietnam becomes a permanent reference point, a reminder of what happens when theory meets jungle, heat, fear, and necessity. The irony is quiet and unavoidable. America did not rewrite aircraft structural engineering because it wanted better airplanes. It rewrote it because imperfect ones kept bringing pilots home, until suddenly, one didn't. That unpredictability was unacceptable. So the rules changed. They never changed back. Today, every military aircraft and nearly every civilian airliner carries Vietnam in its bones, in its crack arrest features, in its inspection ports, in its fatigue models that assume chaos instead of order. The jungle is gone. The war is history, but the lesson remains. Metal does not care what you assumed. Combat does not care what you calculated. Only structures that expect damage and are honest about it deserve to fly. August 9, 1981, Edwards Air Force Base, California. A brand new aircraft lifts off into the desert sky. Its skin is clean, its systems pristine, its pilots confident. But beneath the paint and composite panels, this aircraft is carrying scars from a war it never flew. Engineers watch from the control room as telemetry streams across their screens. Load paths, stress distributions, fatigue counters ticking upward with every maneuver. The data matters now because someone, years earlier, learned what happens when it doesn't. Every modern aircraft test program traces its lineage back to Vietnam, not symbolically, literally. Damage tolerance requirements in military specifications, fracture mechanics embedded in certification standards, full-scale fatigue testing that includes simulated battle damage. Inspection regimes designed around the assumption that cracks already exist. None of this was standard before Southeast Asia. Vietnam forced aviation engineering to abandon optimism. In its place came realism. Aircraft are no longer designed to be flawless. They are designed to be forgiving. Forgiving of corrosion, forgiving of misuse, forgiving of damage inflicted at the worst possible moment. The legacy is everywhere, in the A-10's ability to fly with half a wing destroyed, in the F-16's blended fuselage designed to distribute stress after damage, in civilian airliners built to survive explosive decompression without structural collapse. These are not abstract improvements. They are direct descendants of cracked Phantoms, overstressed Hueys, and Thunder Chiefs that came home one time too many. Vietnam taught engineers something combat pilots had always known: that survival is not about perfection, it is about margin. Margin against fear, against bad weather, against bad luck, against the unknown stress you didn't calculate. The men who flew those missions rarely knew they were changing aviation. They just wanted their aircraft to hold together long enough to land. But every time one did, every time metal bent instead of snapping, it rewrote what engineers believed possible. Today, when a pilot brings home a damaged aircraft, when a mechanic finds a crack before it grows fatal, when a passenger jet flies millions of hours without structural failure, Vietnam is there. Quiet, uncredited, indelible. Because the most important engineering rules are not written in classrooms. They are written when reality refuses to follow theory and forces you to listen.